Hello friend, welcome to ashatech.com. Today in our series of mechanical engineering science, we have some questions that we are going to answer. Question 1 says, with the aid of a load extension graph, derive an expression for strain energy during gradual loading. Part B says, a steel strut of a square section 120 mm by 120 mm over the middle part of length of 150 long and 90 by 90 mm over the remainder of its length. If the total length is 250 millimeters and load is 900 kilonewtons, calculate the total strain energy in the bar. We are taking E modulus of elasticity as 200 giganewton per square meter. Now to solve this problem, I want us to define what strain energy is, and this is the energy which is stored within a material when work has been done on it. It could be stretching, it could be compressing it. So whatever work is done on a material and the energy is stored in it, then we shall say the energy stored in it is strain energy. Now, according to our question, we want to derive the strain energy on a material that is undergoing gradual loading. So if we consider a bar of cross-section area A, the elemental length of it being the S, a small length of it being the S, then considering a load P which is stretching the material, then if we are to look at the load, if we are to plot values of load against extension, each load gives a particular extension. Each load gives a particular extension. Then we draw a graph of load against extension. It would give us a straight line that passes through the origin. And line OB is the one which is going to, when we draw a line OB, then anywhere on the extension graph, when we draw a straight line, then the area under this graph is the one that is going to give us the work done, and this is going to equal to the strain energy. So here it has been assumed that the material remains elastic whilst work is being done on it, so that all the energy is recoverable and no permanent deformation occurs due to yielding of the material. Now, if the weight of the bar is neglected, let us consider a small element of the bar, length the S shown in the figure above. If the graph of load against elastic extension is plotted, then the shaded area under the graph is the one that will give us the work done, and therefore the strain energy. Therefore, if we can recall a work strain energy stored in an elastic material, for example spring, we said that work is equal to force times distance, which is extension x, but this force for an elastic material that obeys Hooke's law, it is equal to kx, so times x. So if we take half of that force, then it will be a half kx squared. Now, in this particular regard, we are using P as the force. So since this is an elastic material that does not change over the entire area, then we shall take half the average of this force, then times the extension of that material. Therefore, it will be U equal to a half P times small change in dimensions, which is extension. What about modulus of elasticity of this particular bar? It is equal to stress out of strain. But stress is equal to force out of area, and the strain is that extension or the change in length divided by the original length. Here the original length, because we are taking the small element, then the original length is going to be the s. The change in that length is sigma. Therefore, Young's modulus or modulus of elasticity will equal to P ds out of A times the extension, and therefore the extension will be P ds divided by AE. Now that is equation 1. That is equation 2. We have also equation 1. Now equation 1 is a half P times sigma. Then equation 2 says sigma is equal to P ds out of AE. Now, strain energy for this bar, therefore, if we substitute equation 2 in equation 1, it means a half times P, which is in the equation, times the extension, which is P ds out of AE. Therefore, U will equal to P squared ds divided by 2 AE. Total strain energy for the bar over the entire length L will equal to, therefore, by integration, it will be U equal to, actually this one I can call it du, so that it is that small strain energy, so that for us to get the total energy, we integrate that du. Therefore, it becomes U equal to integral from 0 to L of P squared ds to AE. This would give you P squared times S divided by 2e. If we substitute in the limits, then finally our total strain energy would give us P squared L divided by 2AE, whereby P is the load, L is the length, A is the cross-section of the bar, and E is the modulus of elasticity of the material of the bar. And so, if the area of the bar remains constant over the length, then U will equal to P squared L out of AE. And this is the expression for strain energy in gradual loading. So that one is over. Now let us look at part 2. Part 2 gives us a bar that changes over over its length. One section, one part of half of it, half of the length, has a section of 120 by 120. Again, another half has a cross-section of 90 millimeter by 90 millimeters, and it is holding a force of 900 kilonewtons, which is a tensile. Now, our task is to find the cross-section area of A. This bigger part is 120. Length by length, or just side times side, so that becomes 120 times 120 times 10 to the power negative 6 to convert these figures into meters, and this would give us 14400 exponent negative 6 square meters. Then small a for the other cross section, it is of 90 millimeters, so it will be 90 times 90 times 10 to the power negative 3 times 10 to the power negative 3, which gives you 10 to the power negative 6. We are converting it to meters, each section to meters. Therefore, we will have 8,100 times 10 to the power negative 6 square meters. Load P is given also as 900 times 10 to the power 3 newtons. E, which is the modulus of elasticity, is 200 times 10 to the power 9 newton per square meter. Then what about the length of A? The bigger part is 75 times 10 to the power negative 3, because the total length is 150. So 150 divided by 2, which is halfway of one section, halfway of the other, then it means length that has a bigger section is 75 times 10 to the power negative 3 meters. For the small section is also 75 times 10 to the power negative 3 meters. Now our task is to calculate the strain energy as a result of that loading. Now we have already derived this expression that strain energy is equal to U, which is P squared times L divided by 2 AE. Now, because there are different sections, so we are going to divide it, the strain energy for part A strain energy for the small section. This will, if I factorize out P squared out of 2E outside, it will be P squared out of 2E into 75, which is the arrow length of the bigger section, times 10 to the power negative 3, divided by the area, the cross-section area of the bigger section, 14400 times 10 to the power negative 6, plus 75 also times 10 to the power negative 3, divided by 8100 times 10 to the power negative 6. This is to the power negative 6, to the power negative 6, to convert them, of course, as we have already calculated, into square meters. Therefore, U will equal to, we already know P as 900 kilonewtons, so we square it, divided by twice the Young's modulus, which is 200 times 10 to the power 9 for steel, and open brackets 5.208 plus 9.259, and this would give us 29.296 Newton meter, or just 29.296. Thank you so much for watching. Thank you so much for watching.